The second lesson in Chapter 10 used combinations and the binomial theorem. We're splitting this lesson into 2 days and we'll focus on combinations today. This is the last kind of button on your calculator that we will utilize. Here's an example when you'll know it's a combination. If you have 10 books at home and want to bring 3 of them to read on a vacation, how many different sets of books can you bring? So it doesn't say which one you read first, second, or third. That means order does not matter. And because of that, we're going to use the combinations function on your calculator, not the permutation function. We still need to know how many we're picking from and how many we're selecting. And the formula you'll notice is very similar to permutations. We have n factorial on top, and then we have that n minus r factorial on the bottom, but we also have another r factorial. So this eliminates specific orders. Again, because you won't have to read that in first, second, or third order. I'm also going to put that denominator in a bracket. It'll make a difference in your final answer when you have 2 parts in that denominator. For the problem up above, there are 10 books to pick from. This means n equals 10. We're choosing 3 to bring with. That means r equals 3. The definition then of 10c3 is equal to 10 factorial divided by 10 minus 3 factorial, 3 factorial. I'm going to put that in a big bracket. If I simplify 10 factorial, that would give us 7 factorial, 3 factorial, and again, that needs to go in that bracket. If you enter that all in at once, you would get 120 different groups of 3, or different sets. You can also type this into your calculator as well, but again, like I said in the permutation part of 10.1, make sure you can explain the definition. Combinations can be pretty tricky, so it's really important to pay attention in this lesson. A standard deck of 52 playing cards consists of 4 suits with 13 different cards in each suit. We looked at this before we started 10.1. How many 5-card hands are possible if order isn't important? Well, we know that there are 52 cards to pick from, and we want 5 of them in our hand. If you type this in 52 NCR and then 5, write out, and it's not a squiggly equals, it's an exact. Write out how many different 5-card hands are possible. Make sure to plug it into your calculator to check it. Here's why. You're going to get 2,598,960 different 5-card hands. That's a lot to pick from. But when you get more specific, that number will get smaller. Here's what I mean. How many 5-card hands are all 5 cards of the same color? So you could have red or black. For red hands, there are 20, for a red set of 5 cards, there are 26 to pick from, and you would want 5 of them. So just for red cards alone, 26 C5 are the total number of 5-card hands that are all red. But black cards, it's the same setup. There are still 26 cards to pick from, and we want 5 of them. So we're going to do this formula twice. And then to get our total, we'll add them together. That means we have 65,780 for 26 C5. And if I add that to itself, we're going to get 131,560 different hands that are all the same color. And last but not least, at the bottom, this one's really tricky, so I need you to really focus on this section right here. And here's why. How many 5-card hands have at least 1 spade? So that's tricky, at least 1 spade. All right, so we're going to start with this. If our 5-card hand has just 1 spade, that means there are 13 to pick from, and we want just 1 of them. But we have a 5-card hand, not just a 1-card hand. So now I have to think about, well, how many cards aren't spades for the cards I need left over? There are 39 cards that aren't spades, and I would need 4 of those cards in my hand. Okay, 2 spades. Again, there are 13 cards that are spades, but then I need 3 more cards that aren't spades. See how this is kind of tricky? We're going to keep going on until we get all the way up to all 5 cards being spades in our hand. 3 spades means out of the 13 that are possible, we want 3 of them. But then we have to have 2 other cards in our hand that aren't spades. Okay, 2 more. 4 means we have 13C4, and then we want just 1 other card that isn't a spade. And then for the 5, that means all of our cards in our hand are spades. There aren't any that aren't spades. So not only do you have to type this in as a product for each row, but then we have to add the result next to it. I'm going to let you type all this in because it's important to know that you can do that. And then enter that in and then press equals. Pause the video, type all of that in. When you're done, press play and see if you got the right result. It's important to be able to do this independently, so definitely give it a try. If you type it in correctly, you should have 2,023,203 different hands, different 5-card hands that have at least 1 spade in them. That's a pretty significant amount. Let's try a few more. The more particular we get, the less the amount is that we'll have total. D, what's a 5-card hand that's possible with 1 ace and 4 cards that aren't aces? Well, let's start with the aces first. There are 4 aces, and we only want 1. Cards that are not aces, there would be 48 cards that aren't aces, and we want 4 of those. Oopsie, that's an R, not an N. That should be an R right there. So what this means for both of these events to happen, because we want a 5-card hand total, we're going to do 4C1 for all the different ways we could get just one of those aces times 48C4. Oop, there should be a 4 right there. Because we want 4 cards that aren't aces. Type that into your calculator and see what you get. You should get 778,320 hands. So that's a 5-card hand that has 1 ace in it and 4 cards that aren't aces. All right, 5 face cards. That seems simple enough. Remember we talked before, how many face cards are there in a deck? That's these 3 columns right here. That means n equals 12. And I just want straight up 5 face cards. I don't want any other types to work with, so all 5 of them will be those face cards. 12C5 then is only 792. But think about that. There are 792 different 5-card hands you could have that have just face cards in them. It still is kind of a lot. Let's try another one. 4 kings and 1 other card. Now that's not a very likely hand to get. To get all 4 kings and 1 other card, so let's see how this one will go. 4 kings. Well, there's only 4 kings to pick from, and we want all 4 of them. But 1 other card, well, if 4 cards are kings, that means 48 of them aren't kings, and I only want 1 more for my 5-card hand. To get the total, we'll do 4C4 for the kings, and then 48C1 for the other card. Enter all of that into your calculator at once, and guess what? There are only 48 hands where this would be true. Last one. 5 hearts or 5 diamonds. Well, if we just kind of split this up into one at a time, there are 5, or if there are hearts only, there are 13 hearts in the deck, and we would want all 5 of them in our hand. But for diamonds, it's the same rule. There are 13 total, and we want all 5 of them to possibly be diamonds. To figure this one out, the word or means we're going to combine them differently. If we have 13C5, that's all your hand can have. So we're not going to multiply to the other answer, we're going to add it, because this could be true or the diamonds could be true, and then that satisfies that given condition. So we're going to enter those in and add them together. Doing so, you should get 2,574 different hands. So hopefully that gives you an idea of how to work with different 5-card hands given different suits and types of cards in a 52 standard card deck. Let's change gears and try something kind of different. It says William Shakespeare wrote 38 plays that can be divided into 3 genres: Of the 38 total plays, 18 were comedies, 10 were based on histories, and the other 10 were related to tragedies. How many different sets of exactly 2 comedies and 1 tragedy could you read? Notice it doesn't say anything about reading them in first, second, or third order. That means this would be combinations versus permutations. We want 3 total, 2 of them to be comedies. For that part, there were 18 to pick from, and we want 2 of them. And means we're going to multiply 1 tragedy. Well, there were 10 total to pick from, and we want to select 1 to read. To find how many different groups of 3 or different sets of 3 we could read with this kind of material, we would do 18C2 times 10C1. Go ahead and enter that in, 18C2 times 10C1, and write down what you get. When I did this, I got 1,530 different sets of 2 comedies and 1 tragedy that you could read out of William Shakespeare's 38 total plays. All right, last question. How many different sets of at most 3 plays could you read? So now it doesn't matter what type it is. It could be any of the 38. So this means N is 38, but at most 3, what does that mean? That means R could be 3, or at most it could be 2, or 1, or we don't have to read any at all. So the ors mean we're going to separate our choices by adding them together. All right, so if we pick 3, that would be 38C3. That's all the ways we could read exactly 3 plays. And then I'm going to add to that, what if I only read 2? What are all the ways we could select that option? Add again, all the ways we could read just 1. And believe it or not, there is a way that you could actually read no plays at all. It's just one way. You're not reading any of them at all. That means we're going to plug in all of this at once to our calculator. Again, the more you do this, the better prepared you'll be able to be to do this. The better prepared you'll be able to do this independently on your assignment. Entering this all in, you should get a total of 9,178 sets of at most 3 plays that you could read. And that's using combinations in 10.2, Day 1.